Hello everyone. In this video, we want to cover the section or lecture slide for fundamental theorem of calculus. This is the most important theorem in these two calculus courses as it connects derivative and definite integral. So first, let's look at the statement of the theorem. It has two parts. Uh, so first part, it says that if we have an antiderivative of the function f, we can use it to compute a definite integral. First, let me remind you that we have two kind of integrals until now. One of them, it's like this, which is indefinite integral, and it's basically antiderivative, the general antiderivative. It has nothing to do with the Riemann sum or area. The other kind of integral that we have seen is definite integral, which has a lower bound and upper bound. And this is limit of Riemann sum, which is area under the graph. Just looking at the definition of these two, they are completely different. One of them, as I said, it's basically antiderivative. The other one is area under the graph. The importance and the beauty of this fundamental theorem of calculus is how it connects these two. We will find a relationship between them. So now let's go back to the part one. So we have an antiderivative of this function, and we can use it to compute the area under the graph of the function f. So the area under the graph of f between a and b, in other words, definite integral from a to b of f, it's just using the antiderivative and plugging the upper bound first and subtract, plug in the lower bound second. So that's how we can use an antiderivative to compute a definite integral. We invent a notation here because many times we have this process of putting this in a function and putting this in the same function and subtract them from each other. We invent a notation, this notation. This notation, the meaning of it is exactly this. That's plug in the top one first, then minus plugging the bottom. Okay, so this is the first part of fundamental theorem of calculus. In summary, it uses antiderivative to compute a definite integral, to compute area. In the other part, it's the other way. It uses the area to find antiderivative, to create an antiderivative using area. The statement of second part is that if we create an area function like this, which is area, this is area under the graph of f, if this is the graph of f from a to x, from a to x. So we are talking about this area. This area, as you see, a is a fixed number, constant, but x is a variable. So this area depends on x. In other words, it's a function of x. So for any function, we can talk about its derivative. Now we can ask what is derivative of this function with respect to x? And the answer is very simple. It's fx. So in other words, this part is saying that this is antiderivative of this. In other words, derivative of this is that. In other words, we can summarize what we wrote as derivative of integral from a to x ft dt. It's fx. This is the second part of fundamental theorem of calculus. Let me point out a few things. So first, this number, this should be a constant, the bottom lower limit of the integral. Second, this should be a variable that we are actually taking derivative with respect to. And what is the result of derivative? Basically, you can memorize it as taking, when this is constant and this is the variable that you are taking derivative with respect to, it's basically take this and plug it into the integrand, to the function. And you get, plug in x inside f, you get fx. And that's how you can memorize this second part. Let me also mention one last remark about this, and that's maybe for some of you it's confusing why suddenly t appeared. T is nothing special. You can use anything else, like for example, y or w. What's important is that this is the variable of integration that we used t, and this is the upper limit of integral. These two are two different things. And in math, we never use the same letter for two things that are different from each other. So if we call this x, then we cannot use x here. X is already used. You should use another letter. We use t. You can use anything other than x. So that's why suddenly the variable of integration, it's not x, because x is already used as upper limit of the integral. And it's conflict of interest if we use the same letter for two different things. Okay, so summarizing this whole theorem, fundamental theorem of calculus, this part is says that using antiderivative, you can compute area. I can compute this area using the antiderivative f, and that's how I compute it. Part B, it says that you can use area to find an antiderivative. You can use this area function to find the antiderivative. This is an antiderivative of this. So basically, these two parts are saying that antiderivative, this thing, we had two versions. One is antiderivative indefinite integral, and the other one is definite integral, which is area, limit of Riemann sum. So basically, these two theorems, it says that if you can compute this, you can use it to compute the other one. And part two, it says that if you can compute this, you can use it to compute the other one. So basically, there is a close connection between these two. In this sense, you may hear that people says that derivative and definite integral are somehow reverse of each other. In this sense, antiderivative is exactly reverse of derivative, and this theorem connects antiderivative with definite integral. In this sense, there is a close connection between antiderivative, which is reverse of derivative, and area under the graph, or limit of Riemann sum, or definite integral. It is very simple theorem, but it's very, very important and very, very useful. Now let's look at the questions that we have. First, let's do this activity. That is very simple application of the first part of fundamental theorem of calculus. We want to compute an area function, and we use antiderivative to do it. Note that if you didn't have this fundamental theorem of calculus, the way that you need to compute this directly, it's using Riemann sum and taking limit of Riemann sum. So you need to do like the interval 0 to 2, divide it into n pieces, use, for example, Rn or Ln, write down the Riemann sum and compute it, use sigma notation, summation formulas, and take the limit and goes to infinity, as you have seen in previous week and in your assignment. So that's very long way of doing it. Fundamental theorem of calculus give a very fast way of computing this and very easy way of computing this. How do we compute it? To compute this, I need an antiderivative for this. What is antiderivative of this? I have a power rule for antiderivative, which is increase the exponent by 1, divide by the new exponent. Minus, what is antiderivative of 1? It's just x. This function that I wrote is an antiderivative for this function. So I can use this to compute this definite integral. Let's go back and see the statement of first statement. It says that if you have an antiderivative in your hand, you can compute this integral by using this and plugging b and a in the antiderivative and subtract them. Now I use that. So this is the antiderivative. I use it to compute this integral. So that's what I get. The bounds are 0 and 2. I use that notation, that antiderivative evaluated at 2 and 0. What is the meaning of this? The meaning of this notation is plug in 2 in this and then minus plug in 0 in this. So first let me plug in 2. You get 2 cubed over 3 minus 2, then minus plug 0. When you plug 0, you get 0 minus 0, which is 0. So the answer is 8 over 3 minus 2, but 2 is 6 over 3. And in total, you get plus 0 or minus 0 if you like. And in total, this is 2 over 3, which this is the correct answer. Okay, now let's look at this question. This question, I don't like it in this slide because it has nothing to do at all with fundamental theorem of calculus. This should be actually in the previous slides when we define definite integral. This is just about the meaning of definite integral and when it's positive and when it's negative. We are not using fundamental theorem of calculus here. So this question asks which of these definite integrals, in other words, which of these signed area are positive, negative. So we know that if something is above x-axis is counted as a positive in definite integral, and something which is below x-axis, it is negative. So basically what we want is to have part of the function which is negative. Or if we have both positive and negative, the negative part be bigger. So let's check each of them separate one by one. 0 to 3. From 0 to 3, we are talking about this area. This area, it's above x-axis. This is a positive number. So that's not our answer. 7 to 9, the next part, part B. 7 to 9. That we are talking about this area. And this is above x-axis, so it is a positive number. It is not negative. This 5 to 9. Then we have this part, which is negative, this part, which is positive. But which one is bigger? Even visually, it's very obvious that this area is larger than this area. So in total, you have a positive number plus a negative number, but the positive number is larger. So some of them will be positive. So this is also positive. So that's not our answer. Now let's look at the choice D, from 6 to 8. The same scenario. This part, it's positive, and this part, very small part, is negative. But the positive part is much larger, so in total you get a positive answer for this integral. Now this last one, from 2 to 6. Now again we have a positive part and a negative part. But now the negative area, it's the magnitude of it is much larger than the positive area. So sum of these two, one positive and one negative number, will end up to be negative. So this is the correct answer. Again, this had nothing to do with this section actually. It was more about the definition of definite integral. And we didn't use fundamental theorem of calculus in it. Okay, next question is about like understanding the meaning of the area function. Do you remember this was called AX in the fundamental theorem of calculus part 2? the area function. So which of these colored region is the area of them? It's this quantity that we are talking about. This quantity, it's the area under the graph of f from 0 up to x. Which of these is that? Clearly from 0 up to x, area under the graph of f. It's this that we are talking about. So basically, this is integral from 0 to x, ft dt. This was very, I think, a straightforward question. Okay, now the last iClicker question is this one, which is the application of fundamental theorem of calculus part 2. We want to compute derivative of this thing. But look at the thing that we have. This is exactly the like area function. It's like indefinite integral where this is constant. That's very important. This is constant, and this is the variable x that this f prime means derivative with respect to x. This thing that we are computing, it's basically derivative with respect to x of fx. We are computing this. We are taking derivative of this with respect to x, and that's exactly here. So by fundamental theorem of calculus part 2, let me actually rewrite what was fundamental theorem of calculus part 2. It was that if you take derivative from a to x of ft dt, this is constant. This is the variable that you are taking derivative with respect to. Then the answer is very simple. Just take this, plug it into the function. So that's the fundamental theorem of calculus part 2. Using that derivative of this, it's basically take this, plug it instead of t. So if you plug that instead of t, what do you get? You get sine x squared. So the derivative is this one. This was all short answer questions that we had for this section, but we have a lot of activities. Let's do them one by one. This first list of activities is practicing fundamental theorem of calculus part 1. It's using antiderivative to compute these areas, these definite integrals. And the second question, which is here, it's for the part 2 of fundamental theorem of calculus, is taking derivative from an area function. Okay, first let's do this. Okay, to compute the first one, as I mentioned, I don't want to use Riemann sum, limit of Riemann sum to compute this. I want to use fundamental theorem of calculus and antiderivative to compute this. So first, I need to compute antiderivative of this thing. To compute that, note that derivative and antiderivative does not respect multiplication and in particular a square. A square. What is a square? If you have a squared, that's a times a. It's like multiplication. They don't respect that. So you cannot do them, you cannot do antiderivative term by term. That's wrong. Because derivative and hence antiderivative does not respect multiplication. What do we need to do is to expand this expression to have just sum of terms, sum of power terms, and then use a very simple formula for and power rule for antiderivative to find the antiderivatives. So I need to use this formula. A plus b squared is a squared plus 2ab plus b squared. If I apply that formula, I get 1 squared or 1 plus 2 times 1 over x, which is 2 over x, or let me write it 2 times 1 over x. And then I have a b squared, so 1 over x squared, which is 1 over x squared. But to be able to use power rule for antiderivative, I need to rewrite these terms as power terms, not fractions. So rewriting them as power terms, I can say that. Let me write it here. I can say that the first term it's just 1. The second term is 2, 1 over x. Let's just keep it as that because that was exceptional. Antiderivative of 1 over x is ln. I don't need to write it as x minus 1. If you want, you can write it. It's the same thing. But for this one, I want to use power rule. So I write it as x minus 2. Now the antiderivative. The antiderivative of first term. Now I can do term by term. Why? Because it's addition of terms and derivative. Hence, antiderivative respect addition. Derivative of a sum is sum of derivatives. Antiderivative of sum is sum of antiderivatives. Okay, so antiderivative of this, it's just x. Antiderivative of this term, it's ln, we have coefficient 2, I just copy it. Antiderivative of 1 over x is ln. But if it's a general term, I should use ln absolute value x. But here I see the bound is 1 and 2. Between 1 and 2, they are positive. So even if you don't put absolute value here, that's fine. Why? Because the part that I'm using this formula, it's for positive numbers. But for example, let's say this was -3 to -2. Then you necessarily needed absolute value. Otherwise, it was not defined to plug in -2 in ln. So don't forget in the general case, absolute value when you are doing antiderivative of 1 over x. It's ln absolute value x. Then plus antiderivative of this, I use power rule. Increase the exponents by 1, so you get x minus 1. Divide by the new exponent. And now using fundamental theorem of calculus part 1, this antiderivative can be used to compute that integral by plugging 1 and 2 in it. Okay, then the answer is just plug 2 in this and then plug 1 in this and subtract them. Plugging 2, you get 2 plus 2 ln 2, absolute value 2 is 2, and then plus, or no, minus because of this negative sign, and this is 1 over x. So when you plug in 2, you get 1 over 2. Minus plug in 1. You get 1 plus 2 ln absolute value 1 is 1 and ln 1 is 0. Minus 1. When you plug in 1, that's 1 and you have a negative sign, so it's -1. This 1 minus 1, they cancel each other, it's 0. So the answer is basically this. But we can combine these two numbers. 2 minus 1 over 2, it's 3 over 2. So the final answer is 3 over 2 plus 2 ln 2. Okay, great. Now let's do part B, which is very similar. Again, you cannot do antiderivative term by term. Why? Because of this division. Derivative or antiderivative does not respect division or multiplication. So what you need to do, you need to rewrite this term in terms of sum of power terms, similar to what we did here. Here we expanded. Now we need to separate this fraction into these three parts, and then each becomes a power term. So let me write it here. Integral from 1 to 4. So I write this. First, let's notice that this, you can combine them. X times root x. Root x is x 1 over 2. And x times that, it's x, you combine the exponents by adding them. It's x1 plus 1 over 2, which is 3 over 2. So these two together in the denominator, it's basically x3 over 2, if you like. Now let's do this plus this plus this. So first I have 1 over x 3 over 2. Then I have 3x over x 3 over 2 plus x squared over x 3 over 2. Now I simplify all these to write them as a single power term for each term. So this one, I bring it to top and I get a negative sign in the exponent. So x negative 3 over 2. This one, I use the exponent rule, that's x1. So I get plus 3x 1 minus 3 over 2. What is 1 minus 3 over 2? It's 1 over 2. Negative 1 over 2. So this is negative 1 over 2. And the last term, it's this x to the exponent, this minus this. So 2 minus 3 over 2. What is 2 minus 3 over 2? It's 2 minus 1 and half. It's half or 1 over 2. So this is 1 over 2. Now I can compute the antiderivative of this term and use it to compute this area or this definite integral. All these things that we are doing using antiderivative to compute a definite integral are the same here. It's fundamental theorem of calculus part 1. If you like, I can say at this step I used fundamental theorem of calculus part 1. At this step also I'm using fundamental theorem of calculus part 1. So antiderivative of this. Increase the exponent by 1, adding 1 to negative 1 and half, it becomes negative half. Then divide by the new exponent. The same for this. Plus 3, add 1 to this, it becomes positive 1 over 2. And then divide by the new exponents. And finally for this, add 1, you get 3 over 2, divide by the new exponent. And then I need to plug 1, evaluate at 1 and 4. Let me do this, the rest of computation on the next page. So up to now, we got that this is that. Okay, the rest is just putting 4 in this minus 1 in this. Okay. So putting 4, or if you like, I can simplify first and then plug in the numbers. Then I need a little bit more space, so let me bring it all the way up. And I'm doing this computation here. So this is negative first, and then this 2 comes up. It's 2, and then so it's negative 2. And this is root x in the denominator. Plus this 2 comes up and it becomes 6 root x. And this term it's 2 over 3 x root x. This is the same as x root x because basically that's the thing that I explained here. Okay, now I plug in 1 and 4 in this. When you plug 4, you get negative 2 over root 4. Root 4 is 2. Plus 6 root 4. Root 4 is 2. Plus 2 over 3. 4 times root 4, which is 2. Minus plug in 1. When you plug in 1, you get negative 2 plus 6 plus 2 over 3. Okay, then I have minus 1 plus 12 Uh, and this term it's 16 over 3. And this is, let me apply this negative sign to all terms. First, let me simplify this. That's 4. And then apply negative sign, minus 4. And then a minus sign also applies to 2 over 3, minus 2 over 3. Since these two have 4 over 3, let me combine them and let me compute these as well. So that's 11 minus 4, which is 7. And this is 16 minus 2, which is 14 over 3. And finally, to compute the whole thing, let's take the common denominator. That's 21 over 3 minus 14 over 3, which is minus or plus. This was, where is it? This is plus. Yeah, 16 minus 2, which is 14. Okay, so 21 plus 14, that's 35 over 3. And this is the final answer. And for the last one, I probably need a little bit more space. So let me do it on the next slide. I'm doing integral from 0 to pi over 4 cosine 2x plus secant squared x dx. First, let's compute the antiderivative. I'm using fundamental theorem of calculus part 1. I want to compute antiderivative and use it to compute this definite integral, this area. This term, it's easier. So first, let me write antiderivative of that term. So I need to write antiderivative here. And then I'll evaluate at 0 and pi over 4. So antiderivative of this, it's simpler. I recognize secant squared as derivative of tangent. So antiderivative of secant squared is just tangent. Now let's discuss this. Let me explain antiderivative of that here on the bottom. So I want to find antiderivative of this. Basically, I want to find something whose derivative is cos 2x. I want to find the question mark, and I need to write the question mark here. So what function its derivative is cos 2x? First, just the type of the function. It's cos. And I know that derivative of something which is cos is sine. I know that derivative of sine is cos, but the angle, the inside of the function is 2x. So let me try sine 2x and see what do I get. What is derivative of sine 2x? Why I'm trying this? First, I look at the cosine and I know that I need to have sine, which after taking derivative, it becomes cosine. And this inside, it's 2x. So it should be sine 2x. Let's see what is derivative of sine 2x. If you use chain rule, that's derivative of outer function evaluated at inner function times derivative of inner function. So I found that derivative of this is this, but what I wanted was only this without this. So now what do I do? As I mentioned multiple times before, the coefficient, it's very easy to handle. You can just adjust the coefficients as you like. So basically, I can divide by 2 to get rid of this. So divide this whole equation by 2, then you get sine 2x, or if you like, half of sine 2x. It's half of this. But what is half of this? This divide 2, these 2 cancels, and I get exactly what I wanted. So I found my answer. I wanted question mark such that its derivative is cos 2x. Why? Because I have cos 2x. I want to find antiderivative of it. So I found antiderivative. Cos 2x is derivative of this thing. This thing. So that's antiderivative of cos 2x. Let me write it in the parenthesis above. Half of sine 2x. Now, the final step is just evaluating. Plug in pi over 4 first, top one first, minus the bottom one. Okay, first pi over 4, you get sine pi over 4 times 2. That's pi over 2. Plus tangent pi over 4. This is when I plug in pi over 4, then minus plug in 0. It's sine 0 plus tan 0. What is sine 0 and tan 0? If I draw a unit circle here, this is sine axis, this is cos axis, and for first angle 0, it's here. As I see, the y coordinate of this point is 0, so sine is 0, so this is 0. And tangent is sine over cosine. So this is also 0. It's sine 0 over cos 0, which is 0, because sine 0 is 0. Now sine pi over 2. Now I'm here. Pi over 2. As I see, y coordinate of this point, it's 1. Radius of this, it's unit circle. Radius is 1. So sine pi over 2, it's 1. So this is 1. And finally, tangent pi over 4. Pi over 4, it's 45 degrees. And I should read it from the special triangle. A special triangle that you should already know or memorized. One of them, it's this triangle. 45 degrees, 45 degrees, 90 degrees. Tangent is opposite over adjacent, so it's 1 over 1, which is 1. So tangent pi over 4 is 1. Now, I have very simple computation. 1 over 2 times 1, which is 1 over 2, plus 1 minus 0. So in total, I get 3 over 2. That's the final answer. So all these 3 questions were using antiderivative to compute area of the given area or the given definite integral. Note that without fundamental theorem of calculus, the way to do these were using Riemann sum and taking limit of Riemann sum. See how important the fundamental theorem of calculus is. It simplifies the computation a lot. Okay, so that's why it's the most important theorem in these two courses. And because it's actually connection between two fundamental things that you study in calculus. One is derivative, the other one is area under the graph, limit of Riemann sum, definite integral. The connection between these two things, derivative and definite integral, is given by fundamental theorem of calculus. Okay, now let's do this last activity, which is about fundamental theorem of calculus, part 2. So before doing this, I like to do this example in the most general case, and then I use the result that I get to give the answer of this question. I'll do all these steps that are mentioned, but for a general case. So I already know that fundamental theorem of, let me explain the general case here. I know that fundamental theorem of calculus, part 2, it's saying that derivative with respect to x from, if it's the lower bound is constant, the upper bound is the same as variable of the that you are taking derivative. Don't use the same variable x here because that's different. We don't use the same name twice. So you should use something else. It can be anything if you like. Any letter that you like, put it instead of t and here. That's the same thing. Okay, then this derivative is take this and plug it into the function. So it's fx. Okay, that's fundamental theorem of calculus part 2 itself. Now let's discuss what is derivative of, now my question is, what is derivative of similar thing, but instead of having just x here, having a function of x. Let's say gx. Now I want to answer the question that what is derivative of this? Note that our question is this. It's a special case of this. This is our f function, and this is constant. And here, instead of x, I have x cubed, a function of x. So let me do the computation because it's the same computation. Let me do it in the general case and then find a formula that I can use for this. Okay, to do this, it's basically what we need is again fundamental theorem of calculus part 2, but instead of x, I have a function of x. This reminds me of something. In previous course, differential calculus, we learned that if you know how to compute derivative of, for example, a function, like let's say this function, you know how to compute derivative of it. You have its derivative. Now I replace the variable x with another function. I have a composition of two functions. Then I had a rule for derivative that gave me the opportunity to compute the derivative of now this new function, which is composition of two different functions. Basically, this is the case now. If I replace this with gx, it's my question. So basically, it's this thing combined with chain rule. Let me explain it in more details. It's as easy as this, but to make it more clear for you, let me give a name to different things. So first, let's define or give a name to this function. Let's say ax. It's integral from a to x, ft dt. I know from fundamental theorem of calculus part 2 that derivative of this function is fx. Let me also write this down. By fundamental theorem of calculus part 2, a prime x is fx. But what I have is, instead of the input x, the variable x, I'm replacing it with gx. Basically, the thing that I have here, it's AGX, replacing every instance of X with GX. What do you get? You get this. So basically, this question that I'm talking about, it's a derivative of this thing. So my question to compute is basically derivative of this. Note that this, again, it's okay. This thing that I'm taking derivative from it, this inside parenthesis is the same as this. The thing that I'm taking derivative from. It's basically this, but instead of x, I need to replace gx. So if you replace instead of x, gx, you have a inside gx, a evaluated at gx, or a composed with g. So now this is very familiar to you. That's taking derivative of a composition of two function. So that's chain rule. By chain rule, here I'm using chain rule. The answer is a prime gx, a derivative of outer function evaluated at inside, times derivative of inner function. But I have a prime. What is a prime? It's this. By fundamental theorem of calculus part 2. So now by fundamental theorem of calculus part 2, this thing that I have here, I need to a prime is f. So I need to replace this with lowercase f. Or let's use dot as multiplication to be more clear. This. So basically I found a formula. Let me write down, this is basically the solution, end of solution for this, computing this. The answer is this. But let me write it as the result, final result that I got is this. So it's very similar to this. What was this? This was saying that if this is constant and this is a variable that you are taking derivative, then the derivative is plug this inside this. For this, basically, it's saying that this should be a still constant, and this is a function of the variable that we are taking derivative. Then, because of chain rule, it's not just plug in. It's plug-in. Plug-in part is this part, this term. It has extra term of derivative of the function that we have here. So basically, the way that I can memorize this is derivative of such thing is take this, plug it in this, that's what you get here, and then times derivative of this itself. Derivative of outer function evaluated at inside, then times derivative of inside. Don't forget about derivative of inside. So this is the inside of the function. So the derivative of that comes after. Okay, now let me use this result to answer this question. Basically, if you like to do this question independently, you need to repeat this process that I did for that particular f and this particular g. But let me use this formula. Instead of writing this again, this whole process again, let me use this final answer that I got. So what is derivative of f prime? What is derivative of this? In other words, what I'm computing, what is derivative with respect to x of integral from 3 to x cubed ln 1 plus 2t dt. I'm computing x cubed. What is this derivative? I first check, oh, that's constant. This, it's not exactly x. It's x cubed. So I need to use chain rule. Hence, by fundamental theorem of calculus, first I plug this inside, and then because of chain rule, I also have derivative of this coming after. So the answer is take this, plug it in this. You get ln 1 plus 2x cubed. This is just taking this, plug it in this. But I'm not done. By chain rule, I need also to multiply by derivative of the inner function. I need to multiply by derivative of this as well. So derivative of that is 3x squared. So that's the final answer. Basically, the final answer is 3x squared ln 1 plus 2x cubed. As simple as this.